Assalamualaikum warahmatullahi wabarakatuh. I am Nurul Izzati binti Dar Azman. Today I want to share about my final year project which entitled Application, Prospect and Challenge of Fiber Optic Sensors. This project is supervised by Sir Muhammad Firdaus bin Osman. The study will be conducted based on the following objective. First, to review the information capacity of effectiveness of fiber optic sensors. Second, to understand the lifetime of the fiber optic sensors. And third is to determine the challenges that are faced by the fiber optic sensors application. Fiber optic sensors. The discovery of the laser in 1960s sparked interest in utilizing fiber optic for transmitting data more efficiently than traditional electrical methods. Despite initial challenges such as significant signal loss, advancement in 1970s led to the creation of low-loss optical fibers which revolutionized the field of communication. As the capacity of optical fibers to transmit large amount of data at the speed of light increased, there were concurrent advancement and cost reduction in optoelectronic components, giving rise to a new product sectors. The fusion of optoelectronic technology with fiber optic telecommunication led to the development of fiber optic sensors. These sensors utilize the nearly lossless nature of optical fiber and their increased sensitivity to change in phase, intensity, and wavelength caused by external disturbance. Fiber optic sensors technology has become a significant user of optoelectronic and fiber optic communication sectors technology. Components originally designed for fiber optic sensors application have also contributed to advancement in the field. As component costs decrease and quality improve, fiber optic sensors have gained the capability to replace conventional sensors. Application of fiber optic sensors. It is divided into three parts which are physical sensing, chemical sensing, and also biomedical sensing. For physical sensing, interferometric based sensors are commonly used to detect minute change in physical parameters by measuring phase shift in interference waveforms. Coarse wavelength division multiplexing (CWDM) can be used to combine free space optics (FSO) communication with a sensor network, enabling simultaneous optical communication and sensing signal transmission. Wavelength monitoring in fiber optic system help maintain signal quality by identifying and resolving issues such as wavelength drift, misalignment, or excessive power swing. There are two examples of physical sensing which are optical performance (OPM) and fiber breadth grating (FG). For optical performance monitoring (OPM), the system rely on wavelength monitoring to evaluate real-time optical signal quality, identify signal deterioration or performance impairment, and take preventive actions. For fiber breadth grating (FBG) sensors, inscribed into the core of fiber optic, offer advantages such as anti-electromagnetic interference, high resolution, sensitivity, and multiplexing capability for measuring temperature variation and stress and strain. For chemical sensing, fiber optic chemical sensors can utilize optical fiber as transmission channel to guide light to and from the detecting area. The light can be modified either by direct interaction with the analyte or through a sensor's device outside the fiber. Chemical detection with optical fibers can be challenging due to the chemical inertness of silica fibers. Transductive element can be used to transform chemical information into easily measurable fiber properties such as strain or temperature or optical transmission. Fiber optic chemical sensors have shown competitive performance in selectivity, sensitivity, and multiplexing capabilities. For example, molecularly implemented polymers combined with surface plasmon resonance have demonstrated good selectivity to specific analytes, and multimode fibers with specific sensing material have achieved high resolution detection. Fluorescence emission is one of the techniques that used in chemical sensing with fiber optic. The fluorescence characteristic of fluorophores can be altered when they interact with analytes, including change in intensity, lifetime, wavelength, or polarization. The third one is biomedical sensing. Fiber bright grating FBG sensors are employed in biomedical application, particularly as force sensors for identifying tissue interface and positioning categories in areas such as the epidural region. FBG sensors offers properties such as biocompatibility, broad bandwidth, and small size that making them suitable for medical application. Optical spectroscopy technique using fiber optic have been implemented in clinical setting for diagnostic application. Flexible catheters with small diameters are used for optical spectroscopy, specifically low coherence enhanced backscattering spectroscopy for the early detection of tumors. Next is the prospect fiber optic sensors. There are three prospects of the fiber optic sensors. The first one is intelligent optical network. Intelligent optical networks are in their early phase and require further development in network configuration, maintenance, and fault detection. Monitoring network parameters is critical due to the significant impact of fiber failure on the economy and society. Future research direction include system parameter monitoring using simplified coherent technology, machine learning, coherent signal analysis, and phase-sensitive optical time-domain reflection, or known as OTDR. The second one is integration technology and system. Integration of device leads to cost reduction and enable high-speed signal transmission over short distance. However, integrating coherent systems faces challenges related to phase and polarization recovery. The capacity of the system can be greatly increased by realizing large-scale integrated optical or known as OEO system. Research direction include advancement in essential components for spatial division multiplexing SDM system, such as integrated ladder and modulators, two-dimensional integrated receivers, and energy-efficient integrated optical amplifiers. The third one is energy efficiency and sustainability. Fiber optic sensors have the potential to create sustainable and low-energy communication systems. Real-time monitoring of factors like temperature, strain, power, and use allow operators to optimize energy usage, reduce waste, and enhance overall system effectiveness. This aligns with the communication sector's increasing focus on sustainable practice and environmentally friendly technologies. Utilizing existing infrastructure such as lighting in smart city can provide high speed, low energy and sustainable network connectivity for various applications, freeing up the RF spectrum for other mobile applications. After that, we go to the challenges of fiber optic sensors. There are three challenges of fiber optic sensors. The first one is fiber cross-section. It can reduce the non-linear effect of high power transmission. Few mode fiber and digital backpropagation DBP technique are used to handle non-linear effects. However, DBP algorithms have limitations in accounting for non-linear effects between channels, leading to increased complexity. The second one is low-loss optical fiber. It is crucial for maintaining signal integrity. Losses in optical fiber can be caused by scattering, absorption, and flaws. Low-loss fiber are manufactured using high-purity silica glass and precise control of the core and cladding design to minimize attenuation. They enable effective and dependable optical communication over long distance. The third one is spectral overlap. In sensor, fiber optic communication system can result in interference and crosstalk. Multiple sensor or sensing device sharing one fiber may have overlapping reflection spectra, make it challenging to extract accurate sensor data. Spectral overlap can limit the resolution, discrimination, and sensitivity of the sensor system, impacting its performance and accuracy. Ongoing research aims to address this limitation and improve sensor system capabilities. In conclusion, fiber optic sensors have great potential in optical communication, improving network performance and security by monitoring various parameters. Ongoing research aims to enhance sensor capabilities and affordability. However, challenges such as nonlinear effect, loss in optical fiber, and spectral reflection overlap need to be addressed through further research and development. These include designing specialized fibers, optimizing manufacturing process, and implementing advanced signal processing techniques. There are a few recommendations for the future. The first one is we need to continue research and development that should focus on designing specialized fibers that can minimize nonlinear effect. The next one is improving the manufacturing process for fiber optic is crucial to minimize signal loss. And the last one is implementing advanced signal processing techniques can mitigate the challenges associated with spectral reflection overlap. So that's all from me. Thank you for watching.